Hey you guys, welcome back to another video. Today we're doing topic 2.3 exponential functions. In math, we study several different types of functions. Three types of functions seem to keep showing up in every math course from Algebra 1 to Calculus. These three families of functions are also featured predominantly on the SAT and the ACT. Those three function types are linear, quadratic, and exponential, and the way to differentiate them is by looking at their exponents. So the highest degree for a linear is 1. So even though they don't have the 1 as the exponent, there is an imaginary 1 there. So the highest degree is 1, and the graph looks like a straight line. It could have a positive slope, or it could have a negative slope like this. Okay, for quadratics, the highest degree is always 2, and we have a parabola either facing up, or it could be facing down like this. The exponential will always have a variable in the exponent. And that's how you can tell that it is exponential. And you can have exponential growth where it goes up like this, or exponential decay where it goes down like that. Okay, exponential functions are some of the most important functions in the real world. They appear in many places, including population growth, money, such as interest and debt, radioactive decay, spread of disease, etc. In addition, the SAT will include several questions that require an understanding of exponential functions. Key characteristics of exponential functions. A represents your initial amount. So they could tell you in words, I introduced this many bacteria into the population from day 0, or graphically, it could be your y-intercept. They give you a graph or a table. B represents your base or the common ratio. So that is just what you multiply to get from one term to the next. They might say the population is tripling every year or something like that. Okay, an exponential function has the general form f of x equals a times b to the power of x, where b is greater than 0 and a and b are constants. A cannot equal 0 and b cannot equal 1. Okay, so what this is saying is that the base is positive. Your base cannot be a negative number. And then also notice that they don't have the or equal to 0. So that means that b cannot equal 0 either. So let's see what would happen if a were equal to 0, because we're saying that there's these three restrictions here. If I were to put 0 here, 0 times b to the power of x would just be 0, because anything times 0 is 0. This is just a constant line at the y-axis. Okay, so y equals 0. Notice that's just a constant horizontal line, which would not produce an exponential function. So that's why a cannot be 0. Let's see what would happen if I make b equal to 0. I would have a times 0 to the power of x, where anything times 0 is 0. So this would still be 0. So again, I would end up with that horizontal line on the y-axis at y equals 0. Again, not producing an exponential function. If b were equal to 1, I would have a times 1 to the power of x. 1 to any power is still going to be 1, and a times 1 is a. So now that means that I have a horizontal line, but it might be somewhere else. It might be at y equals 3 or y equals negative 2. Again, it's still just going to be a constant line, horizontal line. It is not going to produce an exponential function. So that's why all of these restrictions are important, because they ensure that your graph is actually going to end up being exponential. Okay, now there's two types of exponential graphs. You have exponential growth. For exponential growth, your a is greater than 0. So again, this is just saying that your y-intercept is positive. And if your y-intercept is positive, that means that your graph is going to be in the first two quadrants. So it's going to be in the top. Okay, so this is quadrant 1 and quadrant 2. So if your y-intercept is right here and you have a positive a value, then you're going to be in the top two quadrants. Okay, and then this is saying that your base is greater than 1. Additionally, all of the exponential functions have a horizontal asymptote. The parent function has a horizontal asymptote on the x-axis, which is at y equals 0. Okay. Now, if the graph is shifted up or down, that horizontal asymptote could change. Like if I have a HA instead at y equals 3, then all of this would shift up. So the horizontal asymptote can change, but if there's no transformation, the parent function has the horizontal asymptote at 0. Okay, so for exponential growth, you always start on the left and you're going to go up to represent that growth pattern. Okay, then you have exponential decay. Again, your y-intercept is positive. And since it's positive, that means that your graph will be in the top two quadrants. So you can see that even if it's decay, you still have a positive y-intercept there. So that could be anything like 2 or 3 or 4, but it's going to be a positive y-intercept. This space is between 0 and 1. Okay. Now that could be represented as a fraction or as a decimal, but it's important that you analyze your fractions because they're going to try to trick you and give you something like 3 over 2. If your numerator is bigger, it's going to be bigger than 1. So this is actually 1.5, okay? So as opposed to if your numerator is smaller, then you have a number that is less than 1. So you want to make sure you're analyzing the fraction. So don't just assume that because it is a fraction, it's going to be decay. And then for decay, you always start on the left and you're going to work your way downwards to represent that decreasing pattern. Okay. This one also has the horizontal asymptote at y equals 0. Okay. Increasing versus decreasing. Exponential functions are always increasing or always decreasing. They will never switch from one to the other, so they have no relative local extrema. Okay, so always increasing, always decreasing. They have no relative or local extrema. Remember that extrema are maximums and minimums. So this is just saying there will be no maximums or minimums. So notice that this graph is always going up and this graph is always going down. So there is no maximum or minimum. There could be a maximum or minimum if they restrict the domain. So right now, this domain is negative infinity to infinity. So as it is, there is no maximum or minimum, okay? But let's say that I restrict it to right here and I put an endpoint there and I'm saying my domain is negative infinity to positive 4. Okay, let's assume this is 4. Then whatever this y value is would be my maximum. So the only way to have a maximum is if they restrict the domain. Otherwise, there will not be any maximums or minimums. Okay. Exponential functions are always concave up or always concave down. They will never switch concavity, so they have no points of inflection. So notice that both of these make that smiley face for concave up. So you're not going to see a graph that looks like this, how we saw in Unit 1, where you have half of a frown like this and half of a smile like this. So you're not going to have both. It's always going to be either concave up or down. For exponential functions in general form, as the input values increase or decrease without bound, the output values will increase or decrease without bound, or they will approach 0. Okay, so this part here that says as the input values increase or decrease without bound, that means that x is going either to positive infinity or x is going to negative infinity. And if you remember from Unit 1, if you're going to positive infinity, that means you're going all the way to the right. And if you're going to negative infinity, that means you're going all the way to the left. Okay, so if it says without bound, that means you're going to either positive or negative infinity. Okay, and then when it says that output values increase or decrease without bound, that means that the y values are either going up to positive infinity or down to negative infinity. Okay, so as you go to the left or right, you can go up or down to infinity, or you can approach 0. Okay, so that's also an option. So let's look at the exponential growth. So as I'm going to the left, okay, as I'm going over here, notice that this part of the graph, it doesn't represent that it's going up or down all the way to the left. Rather, all the way to the left is going to keep approaching the horizontal asymptote. So on the left, we are going to 0. Okay, so that's because of the horizontal asymptote. And then all the way to the right, notice that this graph is pointing up. So on the right, this graph would go up to positive infinity. As opposed to this one on the left, the graph is pointing upwards to positive infinity. And as I go all the way to the right, notice that this graph is also going to stay approaching the horizontal asymptote. So the right limit is 0. So that means that regardless of what graph you're looking at, you're always going to have one side that is approaching 0 because of the horizontal asymptote, and then one of your limits will always be either positive or negative infinity. So this 0 represents your horizontal asymptote. Now remember that the horizontal asymptote can shift up or down if there is a vertical translation moving the graph up or down a certain number of units. But again, if there's no transformation, it'll always be at 0. So you have three options here, okay? You can go up, you can go down to infinity, or you can approach the horizontal asymptote. All right, one more thing I want to cover is how to graph reflections. So the first thing you're going to do is graph the growth or decay without the reflection. After you have the graph without the reflection, you're going to manually flip it over the x-axis. And just as a note, your reflections are always in quadrants 3 and 4. Okay? So, and this is when your y-intercept is negative. And you'll see that there's a negative in the front. Okay, so let's do an example. Let's say I give you f of x is equal to negative 5 times 3 to the power of x. Okay, so to graph these by hand, you first need to figure out if it's growth or decay. And you do that by looking at the base. So I know that this base is 3. Remember that if your base is greater than 1, it's going to represent growth. So first, you're going to graph the growth in the top quadrants, okay? So that means I need to start low, and then I'm going to go up to represent my growth. And then because there was a negative in the front, I know that I need to reflect it. Okay, so what I'm going to do is literally just flip it. You can use a dashed line so that you can differentiate. So I'm going to do a dashed line here, and I'm just going to reflect it over the x-axis. So this is the one with the reflection. So when you're getting asked questions about what the graph looks like, they might ask you what the limits are, or they might ask you, is it concave up or down? Is it increasing or decreasing? If they have a negative in it, you need to be looking at your reflected graph, okay? And then you can see here that this would have the y-intercept of negative 5. And you see that it's in quadrants 3 and quadrant 4. So if it's negative, it'll be in the bottom quadrants. If your y-intercept is positive, you'll be in the top quadrants, okay? So let's do some examples. Write limit statements for the end behavior of the following exponential functions, okay? So here I see that I have a horizontal asymptote at y equals 0. And I see that this graph on the left is going to continue hovering over the horizontal asymptote. Okay, so for the left limit, I'm going to say the limit as x approaches negative infinity. And then this didn't give me a name. Usually they'll say this is the graph of f or something, but they didn't. So I'm just going to use the general form for an exponential, which is a times b to the power of x. So on the left side, it is approaching 0. Okay, now on the right side, I see that this graph is pointing up. So I'm going to say the limit as x approaches positive infinity, a times b to the power of x is going up to positive infinity. Okay, so again, on the left, we go to 0, and on the right, we're going up to infinity. Now, if you forgot where these come from, remember that on the x-axis, all the way to the left, you have negative infinity, and all the way to the right, you have positive infinity. Okay, let's try B. So again, I see a horizontal asymptote at y equals 0. If I look at the left, I see that this graph is pointing down. So I'm going to say the limit as x approaches negative infinity, a times b to the power of x goes down to negative infinity. But as I go to the right, I see that this graph is getting closer to 0. So my right limit will say the limit as x approaches positive infinity, a times b to the power of x is equal to 0 because it's going to 0. Okay? C, This one, they didn't give us a graph, which means we're going to have to graph it ourselves. The first thing I need to figure out is, does it represent growth or decay by looking at the base? So the base is always the one that is attached to the exponent. So the base is 2/3. 2/3 is smaller than 1, so this is going to represent decay. Okay, and then my y-intercept is positive. So I know I'm going to be in the top 2 quadrants. Okay, so when I'm going to graph this, I need to start on the left, but I'm going to go down. So it's going to look like this. And then my y-intercept, which is at 0, +5. Okay, so notice that on the left, the graph was pointing upwards. So my limit as x approaches -infinity. And this one, they did give me the name. It was called g of x. So I don't need to write a times b to the power of x if they give me the name of the function. So on the left, the graph was pointing up to +infinity. On the right, I have the limit as x approaches +infinity. G of x is equal to 0 because it's going towards the horizontal asymptote at y equals 0. Okay, so notice that for all of them, there's always going to be one side that's going to go towards the horizontal asymptote of 0, and then the other side will either go up or down to positive or negative infinity. Okay, example 2. For each of the following, determine if the exponential function is increasing or decreasing, and if it's concave up or concave down. Okay, so this graph, if I were to finish it, notice that it would make a smile. So I know that this graph has to be concave up. And then if I trace it going from left to right, notice that this graph is going down. So this one has to be decreasing. Okay. For graph B, if I were to finish this, notice that it makes a frown. So this one has to be concave down. And if I were to trace it from left to right, this graph is also pointing down, so it is decreasing. Okay, then we have C. We're going to have to graph this one ourselves. Remember that to graph, you have to look at the base. The base is the one in parentheses attached to the exponent of x, so the base is 4. Because 4 is greater than 1, it's going to represent growth. So to represent the growth, I always start on the left, and I'm going to have to go up to represent the growth. And then the y-intercept, which is positive, would be at 0, 3. Okay, so notice if I were to finish this, it would look like a smile. So this one is concave up. And if I were to trace this one, I would have to go upwards. So this graph is increasing. Okay, so that's a little review of unit 1.1. And we're going to keep doing concavity and increasing or decreasing. So it's a good thing that we learned it already. Okay, last example. Selected values of the function f are shown in the table above. Determine if f could be linear, quadratic, exponential, or none. Okay, so whenever you're given a table and you need to determine a function type, the first thing you need to do is make sure that the values in x, that the changes in x are constant. Okay, so that's what we're going to do now. So how do we get from 1 to 6? We have to add 5. From 6 to 11, add 5. 11 to 16, add 5. These are all plus 5. So now that we've made sure that the changes in x are constant, we can proceed to look at the changes in y. So remember that for linear functions, you have a constant first difference. Okay, and then for quadratic, you have a constant second difference. So let's see if we have a constant first or second difference. To get from 3 to 5, we add 2, 5 to 9 plus 4, 9 to 17 plus 8, and 17 to 33 is plus 16. Okay, those are not constant. Constant means all the same, so this one is not linear. Let's check to see if it could be quadratic. So we're going to repeat this process and see if the second differences are constant. To go from 2 to 4, we add 2, 4 to 8, add 4, and 8 to 16, you add 8. Again, those are not constant, so it's not going to be a quadratic function either. So now what we can do is check to see if it's exponential. So remember, for exponential, you have a common ratio. And remember that the formula for a common ratio is y2 divided by y1. And I always like to start at the bottom to make my little fractions because I feel like it makes it easier and you're less likely to make mistakes. So I'm going to start with the bottom and then put the 1 on top in the denominator. So I have 33 over 17. 17 over 9, 9 over 5, and then 5 over 3. Now, these fractions cannot be reduced and they are not the same, so it appears that it is not exponential either, but I'm actually going to show you something else. So as we have learned it so far, it would appear that it is none of them. But if I put the first differences back up on the screen, notice that these do show a proportional growth pattern. Because to get from 2 to 4, I can multiply 2. 4 times 2 is 8, and 8 times 2 is 16. So even though at first it didn't appear to be exponential, if the first differences show some kind of proportional growth, then that would mean that it is still an exponential function. So sometimes data from an exponential function does not display a proportional growth pattern. This is due to a vertical translation of the function. So if I move the graph up or down, it's going to mess with the y values in such a way that you can't get that ratio as easily. Okay, so let me show you what would happen if I were to subtract 1 from all of these. If I were to subtract 1, let me do it over here. So if I were to do f of x minus 1, I would have 3 minus 1 is 2, 5 minus 1, 4, 8, 16, and 32. Okay, and then if I were to do the ratios here, I could easily see that these are all times 2. So if the graph is shifted up or down any number of units, it'll still show the proportional pattern if you look at the first differences. Okay, so you can add or subtract the constant from the output values to reveal a proportional growth pattern. And if you can find it from the first differences, then that means that the initial function was also exponential. Okay, so for my final answer, I'm going to say the function f of x is exponential because over equal length input value intervals, the first differences of the outputs of f of x change proportionally. Okay, so this is the same explanation that I taught you in lesson 2.2 with the addition of the first differences. Other than that, it's exactly the same. We always say the input values change constantly and the outputs change proportionally. Okay, the only thing is that the proportional growth pattern was revealed through the first differences, and we're going to explore this concept a little bit more when we get to topic 2.5. But yeah, just know that if you do all of this how we have learned it so far, you do the first difference, second difference, you do your common ratios, and none of it is working, just as a last resort, look at the first differences and see if those reveal a proportional growth pattern. And if you do find a common ratio from the first differences, then that means that the initial table was also exponential. Okay, so we'll explore that in 2 lessons, but if you guys have any questions, please let me know, and I will see you guys in the next video. Thank you. Bye.